Hello, everyone. My name is Minghui Wu. I'm a third-year PhD student with Surrey University and NSIRC. It's my pleasure to share my PhD study. My topic is assessing life cycle costs and environmental performance of composite material in aircraft application. My presentation includes 4 parts, which is project introduction, methodology, results and discussion, and the last part is conclusions and future works. I will start with the introduction. Nowadays, we pay more and more attention to reducing the emissions in order to improve and protect the environment. European Union had launched a program, which is NSIRC 2, to cut the aircraft emissions. Under this program, a sub-project named the thermoplastic on door, which aims to manufacture an aircraft door using composite materials to replace the conventional aluminum materials. But there is no corresponding environmental and economic assessment on this door. So in this case, my research aims to bridge this gap by assessing environmental and economic impacts for the composite door. In addition, my research also conducts a comparison analysis between the composite door and the aluminum door. That's the background. Let's move to the methodology. To assess the economic performance of the product, I use life cycle costing method. This flow chart shows how I conduct this analysis. The first step is setting up the scope and the system boundary. And then the cost breakdown model is built based on the production activities. And thirdly, calculate the total cost, and then perform sensitivity analysis and to identify the effectiveness of key factors which influence economic impacts. And last is the results interpretation. For the environmental impact assessment, life cycle assessment method is used. This model I built is based on the standard ISO 1440 and 1444. This analysis is carried out with the support of the Stuctural software. The industry data is used in this model. So those data is not available. The secondary database, such as the eco-event database, is used. And during the mass production analysis, we should consider the labor hours will reduce as we produce more products. This is mainly because the improvement in workers' skills. So to capture this improvement, I use the learning curve method as shown in this figure. This theory says each time the number of units produced doubles, the cumulative average time unit is reduced by a constant. So in generally, the mass production process can be divided into 2 stages, the learning period and the standard period. The direct labor hours required to produce 1 unit decreases rapidly in the learning period and slowly in the standard period. In my research, the labor hours required at the beginning of this standard period is considered as the minimal time required producing 1 unit by a fully skilled worker. This unit, N, is called the endpoint. I developed a method to calculate the endpoint. So you can see N is calculated as the smallest integer, and that satisfies this inequality. And that's the brief summary of the methodology I used. And let's move to the results and the discussion. In this case study, for the LC, the life cycle costing results, I only considered the recurring costs as the data limitation. So the total cost occurred is around 77K euro, including cost of material, labor, energy, and consumable. It can be seen that the most significant cost contribution is caused by labor at around 63% of the total cost. In the mass production, 87% learning curve slope is applied to estimate the direct labor hours of future unit. So we can see the unit photo is the last goal produced before the learning period came to an end. And so we can see the contribution of labor cost in unit photo has reduced to 45%, and leading to the reduction of the total cost to around 52K euro. For life cycle assessment results, and the results and the emission is aggregated for life cycle impact assessment using the impact 2002 method in Simulcron. So this network diagram obtained from the Simulcron, it shows the total environmental impacts produced by each process. So each box presents the process, and the arrows present the flows between the processes. And the thicknesses shows the contribution to the environmental load generated by each process. So from this result, we can see the energy appears to be the hotspot. After life cycle costing and the life cycle assessment, I also performed the sensitivity analysis to study the influence of production locations and the composite waste treatment rules on the environmental impacts. But here I will not go details as time limit. And the same assessment also applied on the conventional door. And the results compared with those for the composite door. We can see the left figure shows the comparison results in terms of the economic performance of the doors. And the vertical axle is the cost, and the horizontal axle is the aluminum door and the composite door. And the different colors means different cost categories. As mentioned, there are 4 categories I considered in total. That's material, consumable, labor, and energy. So from this figure, we can see the aluminum door has a better economic performance, about half of the cost of the composite door. In addition, the labor cost in each door is the highest. Then let's look at the red figure, which is the comparison results in terms of environmental impacts. And the impacts can be measured at the 4 damage categories, which is human health, ecosystem quality, climate change, and the resources. The blue bar is the aluminum door, while the orange is the composite door. So from this figure, we can see all the impact categories in the environmental performance are lower in aluminum door production. And the last part is the conclusion and the future works. And the key conclusions are as follows. Life cycle costing has been performed to estimate the economic performance of the door. And the learning curve has been analysis to predict the unit price of mass production. And the energy use is the hotspot in production system. Local regional supply chains are environmentally feasible than global supply chains. the composite may incur higher environmental impacts. I also discussed the possible costs of the solution. The current work mainly focuses on the production phase. In the future, I will continue on the use and the end-of-life phase to achieve a comprehensive analysis. Okay, thank you for listening. I'm happy to take any questions.
Yeah, many thanks for your presentation. Okay, so let's have a look at the see if there's any questions posted in the Q&A or the chat. Okay, not just yet. So, so please feel free to use that facility. So whilst people are collating their thoughts, just a question for you. In terms of uncertainties, and obviously the numbers that come out from the costing for the aluminium door, how confident, or what's the uncertainty associated with the final cost that comes out? How do you take into account the uncertainties at different stages? Because obviously all those uncertainties in the input variables will have an overall effect on your final answer, won't it?
So I think that it will link to my validation, my results. It's normally used, it's necessary to validate this result through the publications, reports, and all expert consultations. For my research, this is a new product, and all the cost model, and I built based on the standard, and all the data I use have been validated by experts. Another, in addition, I also collect some cost estimation results from some literature regarding some other aircraft components. And the compression results also shows agreement with those publications, and that the labor cost and the material cost take up the majority of the total manufacturing protections.
Okay, so just a follow-on question. So in the development of the composite door, was it just a black metal approach? They just took the existing design and converted it into a composite equivalent?
Yeah, and this new door is just a prototype. Yeah, and it's a conservative design now. And this model I can use also can be used in the future when the design optimized.
Okay, so just a final one. So were there any, did you take into account the costs associated with joining? Because I can appreciate that the joining required in an aluminium or a metallic door will be completely different to a composite door. Did your model take that into account, or did you have information on that?
And for the new door, the composite door, the joining technique used the induction welding to joining the composite material. And for the composite and the metal parts in the composite door, we use mechanical rivets to join it together. Yeah, and I also compare. I also collected this data for between the. I also collected some industrial data for comparing the joining part.
Okay, thank you.
For the composite and the aluminum.
Okay, thank you. And I think there's a question that's come through on the chat, and the question says, how will you gather information for the end of life in terms of material properties? It says it may follow on. It says it may be difficult to weight them, although material experts may be able to help.
Yeah, the end of life phase is ongoing. Yeah, it's quite difficult to collect real data from the companies. And this part, I will use some secondary data, such as some data from publications and some database. And also, I'm thinking to consult some experts and to know the detailed the process for recycling the composite and the metal material.
Okay, excellent. Okay, so many thanks for your presentation. That brings this presentation slot to an end.